That's so cool. That's so cool.
It's okay.
It's going to be amazing. Yes.
Hello.
Hello. Let me call my name. Oh, there we go. Woo-hoo.
Hello, everyone. Welcome to our stream. I'm Mario Garcia. I'm a technical evangelist at Percona. And today we have Charlie Batista, who will talk about setting up a Postgres connection pool. And we also have Edith and Dave, who are also technical evangelists at Percona. Thank you for joining us, Charlie.
Hey everybody. Hey guys. Hey guys out there. I would like to apologize. We're having some technical issues here. And also Dave here, he's having some voice issues, you know.
A big challenge for me, yeah.
Yeah.
Well, you folks have fun. I'll watch it off YouTube. Take care.
Thanks, Dave.
Thank you, Dave. Bye-bye.
Thank you, Dave.
Yeah, I hope you get better, Dave. Yeah. Yeah, today we're going to talk about connection pooling with Postgres, right? So it's a good discussion. We'll try to talk about to understand the reasoning why we usually need connection pool. What are the solutions that we have in the market, and how we can use them, right? So I think that the first thing we need to understand are the reasons why we need the connection pooler, right? So when we think about application and database, the developers and the applications, they will want the more connections that they could have from the database, right? So let's say we have a website and we are selling t-shirts on the website. Well, I would like to have 1 million connections per second on my website, right? So if we could have like 1 million customers selling on our website, that would be really, really good. But we need to think about those numbers. Is the application server able to provide 1 million connections at the same time? What do you guys think? What do you think it is? Is it easy to get a application out there that can have like 1 million users at the same time? Do you think would that be easy? What do you guys think?
It sort of depends on the infrastructure also where our database is, right? How we are going to scale.
Let's think just about the application. Let's forget the database a little bit, and let's think about just the application. We have the application, and let's say the database is able to scale. So from the application perspective, do you think it's easy to get like 1 million users at the same time on the application?
Yeah, recently I was trying Python's multiprocessing, and I think this is a good example to what you're mentioning, because the idea with multiprocessing is that you can use all the resources available in your laptop or any other equipment that you're using for hosting your application. So I think that could be an example of that, and it really would help us to support millions of users doing operations at the same time on our page or our application.
Yeah, that's a really good example. But do you think we're gonna have the 1 million users all at the same time?
Why not? It could.
We could, right? We could, but
Yeah.
usually this is not what happens, right? Usually we have, let's say, when you go for the statistics, you have millions views per hour, million views per minute, million views per second. It doesn't mean all that million users are there at the very same time, right? So because the access they can come concurrently. They might be there, but they might not. Usually, from the application point of view, we don't scale the application for millions of users simultaneously, right? We want to attend a million users, a million connections per second, for example. In a second, we have we have 1,000 microseconds, right? And this is one thing that we need to think about. Usually, we don't use all the resources at the same time, exactly same moment, exactly same time. For one reason is the laws of physics, right? There was this smart guy that he said, two bodies cannot occupy the same space at the same time, right? So we couldn't break this law yet. Doesn't matter how many lawyers we have, we still cannot break that law, right? And this is also valid for computation, right? When the computers when we started with faster CPUs, let's put on this way, we have the illusion that you were doing a lot of process at the same time, right?
Correct.
But it's just a perception. The thing is, we humans are not able to see things that are too fast. We cannot perceive things that happen too fast. So one CPU can only process one thing at a time, right? Doesn't matter if we do it in Python, in C, in Java, whatever language we do, one CPU core can only do one thing at a time, right? So what happens is the smart people from computing, computer science, what they did is, okay, if one CPU core can only do one thing at a time, why don't we slice the period of time? Let's say we get this 100 milliseconds. So we create 100 slices. Every slice is 1 millisecond, for example. So, and then we give for the applications one slice, right? So let's say we have this application, my website, we have one order that it takes 5 milliseconds to be processed. So it will ask for the CPU for, look, I need time to finish my operation. The CPU will give one slice. He's gonna get that slice 1 millisecond. He will work there, and then when he finish, the CPU will get that process and put to sleep. Literally, the process will go there, and okay, I'm gonna sit down here sleeping until I get my moment back to the CPU. And so in this example, this process will use 5 slices, right? So it uses its time, it does something, and then it comes back to sleep. It goes back, work a bit more, comes back to sleep. So after 5 slices, it will finish its operation. But the thing is, what happens if we have 10 other processes working at the same time? So my process goes and uses 1 millisecond, right? Then it's wait for after 9 processes to do another millisecond. And then more 9 processes to do another millisecond. So every step, it waits around 10 seconds between steps. So in this case, it will take around 50 milliseconds to finish, 10 times more, right?
Yeah.
But for us, it's still super fast. It looks like that all the 10 processes did everything at the same time, right? Because, well, they all gonna finish in, let's say, 100 milliseconds. All of them gonna finish in 100 milliseconds, maybe a bit more. But we humans cannot perceive things in that time. So our perception is that with all those 10 processes, they finish at the same time.
Yeah.
Right? But it's just perception. For the computer, for the CPU, they didn't work at the same time. With the CPU just sliced the time and gave to every process some amount of the time to work. Those processes worked, and then poof, we see, whoa, yeah, this CPU, I have multi-process thing. That's my OS. It has multi-process, right? And this is the magic that the operational system that works together with the CPU, how they make this to look like one single core of CPU is doing a lot of things at the same time. So we have this impression that we are doing all those processes at the same time, but actually it's not, right? So this is one thing that we need to understand when we go for any multi-process application, the database or the website application, whatever application. When we work with multi-process, we need to start understanding those sort of low levels, how the CPU work, because when the developer or the sysadmin come to DBA and tell the DBA, look, we need 1,000 connections to the database. And the database server only has, 100 CPUs. Let's put it really beefy database servers, but 100 CPUs are a lot, right? We need a lot of money to pay for 100 CPU server on AWS or Google Cloud, right? So it's really good server. So yeah, look, you have 100 CPUs. Why cannot I have like 1,000 connections? Remember, coming back, the box, the server, it cannot give you 1,000 simultaneously connections. So the CPU needs to do the slice for those connections as well, right? Mm-hmm. So in this example, 1,000 connections may not be so bad because, well, if we do a simple math, we have 100 CPU cores, 1,000 connections, every core going to work with 10 connections simultaneously, right? It's not that so bad. But imagine that we have most of our selects or queries of the database, they're really, really fast. So they work in milliseconds, right? So, well, and we have thousands of them every second. That's not a big problem because, well, they are milliseconds, and because we have like this ratio 1 to 10, every core works with 10 connections. That fast. Maybe we add a few milliseconds for each connection. But what happens if we get one select that takes like 1 second or more? One connection that is really slow. This connection that is really slow, it can slow down the whole order of connections. Because this connection will be there, working on the server, and the CPU, the kernel, needs to give more and more slices of time for that only single connection. Mm-hmm. And all the other connections that were faster, now they become slower. Well, if you only have one slow connection, that's okay. You still have 99 cores to work with the other connections, right? So, but eventually you're gonna get slower, and your whole application starts to slow down because you have too many connections to your database. So because your database is slower and your application is slower, what happens is you need more connections from the application point of view. Because, well, the application cannot get the data from the database fast enough. You need more connection. And the sysadmin come to you for, look, the application is really slow. Can we get more connection, like more 1,000 connections? Well, we give them more 1,000 connections. Now we have 2,000 connections. What's going to happen is that extra 1,000 connections going to make the database even slower. So the queries that before were taking a few milliseconds, now they're going to take double the time, maybe triple the time. And the application will ask for more connections because now the application is even more slower. So, and then we get into this bad cycle that the application always need more and more connection, and the database cannot provide the information fast enough. And this is the time that we realize, well, what happens if we put something in front of the database that will protect the database to having so many connections? Because for the application, it doesn't matter if we have one connection or if we have 1,000 connections. If it can get the data fast enough using only one connection, why not, right? So we're getting the data as fast as we can with only one connection. If we need more connection, let's say if we need 100 connections to get the data as fast as we can, that's fine. So this is actually a change in paradigm. Instead of looking for the database as number of connections, we look to the database as how fast I can pull the data from my database. And the number of connections really impacts how fast we can pull the data from the database. So usually there is this magic number around the number of connections around twice, 3 times the number of CPUs that you have. Usually works well. When you put more connections than 3, 4 times the number of CPUs you have, then your database starts working really slow. It slows down. And the more connection you put, the slower the database goes. And the slower the application goes. And the perception that we have is we need more connection. But actually, we need less connection. We need to remove a lot of connections. Because another thing that we need to understand is when the CPU puts one process to sleep, let's go back to my process that needs 5 slices of time. So after my process finish its first slice of time, okay, it was granted to work for 1 millisecond. It worked there. When it's finished and the CPU puts to sleep, the CPU needs to do one thing that called context switch. Because remember, my application was working, right? So it has all the data in cache memory. Because we are always worried about how slow the disk is, right? Because we always believe the memory is a lot faster than the disk, right? So we want to put more data as we can in memory. But the thing is, the memory is still slow. If we think about CPU, the memory is a lot, like really, really slower than the CPU. So the CPU uses memory as a big storage area, but it doesn't really work with the data that is in memory. So the CPU goes to the memory, gets all the data it needs to work, put in its own cache. We have the L1, L2, L3 caches. So the closer the caches are the CPU, the faster they are. And then the CPU works with that data. So, but the cache there is small. What happens is when the CPU needs to pull more data from the memory, so it needs to release that data in cache. It saves that data back to the memory and then get more data to the memory works. So put that data back. And this is what happens when the process stops working there. The CPU needs to archive or save that state. Everything that is in cache, everything that is on CPU needs to be saved. So it saves everything there and then allows the other process to start working, the other application to start working. So this we call context switching. So it was working with my application. So my application ran out of time, and then it will allow Edith's application to work. So it needs to save everything that my application was working, save back in memory. And then when Edith's application comes to the CPU, Edith's CPU needs to get all the data that Edith's application needs and start working. So when Edith's application runs out of time and then Mario's application comes to work, the CPU needs to do the same thing. It will get Edith's application, save all the data, everything, all the references, put in memory. Mario's application starts working. So when Mario's application finishes or runs out of time, my application comes back. So my applications need to go, the CPU needs to go to the memory. Remember everything it saved before. It gets from the memory, put here, and start working again. So this switching from process, we call context switching. This switching, it takes time as well, because it needs to save the state, it needs to get new data. So there are a lot of things the CPU needs to do. It costs CPU cycles. So, and this slows down the operations. If we have just a few processes for each CPU core, that's okay. We usually don't feel that time waste. If we have thousands of processes that needs to be switched all the time, we may spend more time in process switching than working. The CPU may spend more time like just changing from one process to another process than working. And this is when we feel the application is stalling. The queries is now, look, the query is super slow. What happened? It's now because there are too many context switching on the database. And this is one of the first things that we need to understand, why we need a connection pooling in front of the database. So the connection pooling, let me share my screen here. Screen share here. Where is, so you can see my screen, right?
Yeah.
So this is a base idea that that we can use a connection pool. See, we have the database here. Actually, this is actually not a base. This is a bit more complex. But let's say here, those are the applications. And then we have the proxy in front of the database, right? The application here, they all go to the proxy. And then the proxy send few connections to the database. So we start protecting our database, right? So the first problem that we're solving with the connection pooling or the proxy, whatever name we give to them, is to preventing the database to have too many connections at the same time. So depending on the implementation of the connection pooler, it's a lot easier for the connection pooler to control thousands of connections than the database. Well, we still have the context switching problem from the connection pooling side. But the thing is, as the only thing that the connection pooling needs to do is to receive connection, send to the database, get the data, and send back to the application. So the context switching here won't impact that much, because this operation takes really few cycles of CPU. It's not like if we are going to the disk, doing the whole query, doing the whole operation on the database. This is the first benefit. Even though we have the context switching here on the connection pooling, it's not that we removed them. We have them, but now they are on the connection pooling. And because the work that the connection pooling does is a lot simpler and smaller than the work that the database does, the impact is not that huge. So we can work with this penalty of the context switching here on the connection pooler. So that's the first thing. The second thing is it's expensive to the database to open a new connection. So when some applications, some languages, not applications, some language and some drivers, they implement what they call persistent connection to the database. So they open a connection to the database here. It's like they open a connection to the database and they keep that connection open. They never close, because closing and opening connection to the database every time that you need something to the database is very expensive. So in the case of Postgres, that Postgres uses process, every connection to Postgres is one process, is a bit more expensive than other implementations of database. Because, well, we need to fork a new process when a new connection is created. It's an expensive operation inside of the kernel of the operational system. It's not cheap. So this new process needs to allocate memory and needs to allocate all the resources. So creating a new connection from the database point of view is really, really expensive operations. Sometimes, well, depends on the select, on the query that you have, creating a new connection takes more time than the select itself. So if we can prevent this to create new connections all the time, we can save resources. So that's another interesting thing the connection pooling does. So a connection pooling here will open the many connections will tell to it. Let's say I want 100 connections to my database. So my connection pooling here, in this case, AJ Proxy or PG Bouncer, here is a PG Bouncer, will open 100 connections to my database and keep those 100 connections open. So they will always keep those connections open. So whenever it needs to close one connection, sometimes the memory management of some connection pooling, they're not as good. And sometimes it's just simpler to close a connection and open a new one, to release the garbage in memory and to get everything clean. But the application doesn't see this. It does in background. And connection management, it's another benefit that we get for connection pooling, right? So let's say we have 1,000 connections here. 1,000 connections. As we can see here, I have one primary, right, and 2 replicas in this diagram. So here I'm using Patroni to coordinate this cluster to have high availability. If this primary crashes, this primary goes down here, my connections that are to the connection pooling here, they can keep the connection from the application side. And then, well, all the connections that they've been working here, all the transactions that have been open here, they obviously would be rolled back. So it will, the connection pool will tell the application, hello, we have a problem. We're rolling back this transaction. We need to apply this transaction again. But it doesn't need to drop the connections from the application. And it can already route the new connections to the new primary that's being elected. So we can work with the proxy and the pooler together with other coordination. In our case here, we use Patroni to hide this complexity from the application. The application doesn't need to know all this complexity here behind the connection pooler or the proxy, right? This is another benefit that we get from using a connection pooler or proxy in front of the database, right? We can hide a lot of complexity that we have here when we're implementing all this architecture, all this kind of stuff. The application doesn't need to know. For the application, okay, I'm just connecting to the database. I only need a connection to the database and get my data. I don't care if it's high available, well, actually the application cares that it's high available, but I don't care how the high availability is implemented. It's using Patroni, if it's using another technology, I don't care. I just want to connect to the database and get my data, right? So having a connection pooling here in front of the database helps. Yep.
Yeah, I have one question. Sorry.
Sure.
I know a little bit about databases, but not too much. So this connection pooling is something that we can use also in MySQL and MongoDB?
Yeah, we do.
Mm-hmm.
Exactly. There are some applications, some connection pooling for the other database as well. For example, on the MySQL world, we have ProxySQL, and there are others. But the idea is the same. We can use the pooling in front of any database. like, or even in proprietary databases like Oracle, SQL Server, there are implementations of connection pooling for them as well, right? And the benefits that we get are the same. Like even for database like MySQL that uses threads instead of process to handle connections, they are still expensive. A thread in the kernel to create a thread is not so cheap as people believe that it is compared to create a process, especially on Linux. It's a bit cheaper, but it's still an expensive operation for the Linux kernel to create a new thread, right? So, and the benefits that you have are the same. The context switching that we have are exactly the same. Doesn't matter if it's a process or if it's a thread, right? So inside of the CPU and the slice time, they are all threads. They all slice the same, right? They have priorities and everything, so they work the same. The benefits that we get, it's not only for Postgres, but they are all the same. It's like we're gonna have similar benefits using a connection pooler. And different implementations of database, they have different implementations of connection poolers. And I don't know much about MongoDB, but if not mistaken, the MongoOS, it works very similar to a connection pooling in front of MongoDB. It does the coordination and all this kind of stuff. But, well, I have no property, no knowledge to talk about MongoDB.
Thank you, Charlie.
But yeah, they do.
Yeah, I have another question.
Yep.
What if we have, for example, we have 5 processes that every process is running an amount of SQL queries?
Mm-hmm.
How do we guarantee that the connection to the database is maintained even if the process takes more time than the expected one? How do we guarantee that the connection won't lose at a certain point?
Well, there are some problems that we need to work around, right? So when we work with TCP, we have this feeling that TCP IP is a cable that goes from one end to another end, right? Especially when we see diagrams of people explaining, look, the TCP IP, it's a connection stream, it's opens here and kept open during all time, right? So actually, that's not true. How the communication works between the client and the server. So the protocol will coordinate, right? The protocol is the language that they use. So when we open a connection to the database, that the protocol of that database will tell that database, look, I want you to keep this port open for X amount of time, right? So it will open that, we send the timestamp, and then it will keep open for X amount of time. So if no communication happens in that amount of time, one of the ends might think, okay, the other guy is just that. But before I close, let me send a packet, a ping to the guy to see if he's still alive. So the ends will ping, can be a ICMP packet, can be one packet that's sent by the protocol to the other end, just to ask, hey guy, are you still alive? Still waiting for me to finish? And the guy reply back, well, no, I'm good. I'm still here. I'm still waiting for you to finish. So even when the server is busy processing things, the communication channel is still open. So that connection, the channel is still open. So, and they still keep talking to each other to say, look, I'm still waiting. Can you renew my time ticket? Because you can think about the time expiration as a ticket, right? You get your car, you go to parking, and then you get a ticket for 1 hour. So if your car stays there in the parking lot longer than 1 hour, when this hour expires, you need to go there and get another ticket for another hour, right? And so on and so forth. If you stay there 1 month, that's all fine, as long as you go there and get another ticket and another ticket every amount of time that you agreed to the owner of the parking lot that you go there and get a ticket. If you don't go, the owner can just stall your car and do something, right? So this is usually how it happens on the application, not only database, on the application when you have the connection. So the connection is open, and then every amount of time that is there is an agreement between the two ends. But look, every amount of time I'm gonna come here and get a new ticket to tell you, look, I'm still alive, I'm still alive, I'm still alive, right? It's a simplistic explanation, but this is usually how that works. We have another thing that we have are the timeout configurations, right? Usually you don't want that one select or one operation in your database take, let's say, 10 hours, right? You want your database to give up. If it's running for, like, let's say 3 hours, for now, man, it's running for too long, I'm gonna give up. So it times out, and then it replies to the application for look, man, it takes, like, it's already 3 hours and not even close to finish, I'm giving up, right? So can you take your car out? I need this lot to do something else, right? So this is the timeouts. We have configurations for them. So we have configurations for the timeout connection. Let's say you start opening a connection to the database. Your application goes to the database, knocks the door, and look, I want a new connection. So you send a packet to the database. The database will reply back, okay, if you want a new connection, this is what I need from you. I need username, I need password, I need to know which database you want to connect, and I need more information. The application goes, you type your username, password, and everything, replies back. So this is a three-way communication, right? The application goes to the database asking for a connection. The database replies back to the application saying what it needs to be able to connect, and also what is the protocol, if it's used SSL or not. So the database tells everything about the new connection, what is needed to open a new connection. And then the application replies back with that information. If everything's fine, connection is open, the database user reply back, okay, connection is open. If the password is wrong, the username is wrong, well, the database reply back, nope, it didn't work, something wrong here, it didn't work. For this process to finish, there is a timeout. The database cannot wait forever. Because, for example, one attack, especially on web application, is you send a packet to the web server. The web server reply back, and when the web server reply back, it's wait for you to acknowledge, well, okay, I'm good here, I received the packet. So if you do not acknowledge, and after some time, the server will believe, okay, the packet was lost in between. And what happens? You send another one, and another one, and another one. The attack, one of the network attack on this way is just open the connection and never reply back. Never reply back, right? So the application has attacked the database. Most of the databases, not only Postgres, but most of the databases, they have a timeout for you to finish to the connection. So when you start, if you don't finish until that many seconds, so the connection is immediately dropped, and everything that you send on that channel will be ignored, will be dropped automatically by the kernel. The database will tell the kernel, look, remember that guy that tried to connect to me here on this spot? Yeah. The guy didn't reply. I don't want to hear from him. So everything will be dropped from the database point of view, right? And also there are other timeouts. There is the query timeout. There is idle connection timeout. Like, for example, on this example here that we have persistent connection. So the proxy opens a connection to the database. Proxy will never close this connection. But if this connection stays for too long without no communication, nothing, the database will tell, look, it's a connection is idle. It's open, but nobody is doing anything. After some time, that idle connection will be closed by the database because there's this timeout. So what happens is, before that time, the proxy send a ping saying, oi, to the database. Hi, you good? I'm still here. Hi. So it goes there and get a new ticket from the top, right? So this is what it keeps those connections open indefinitely, right? Because before the timeout happens, the connection puller will get and ping the database. There are many ways. Some connection poolings, they do a select one, other connection poolers do something a bit smarter. But yeah, they always get a new ticket to keep the connection open. For the select, some database, they implement also a timeout for the select. As I mentioned, you don't want your one operation in your database to take forever. You want that operation to finish. So there are timeouts during the operations on the database. But one thing that we need to keep in mind is there are some events that they prevent the timeout to happen. For example, if we have a data corruption, the disk is corrupted, something wrong. So if we have a corruption on the file system or on the disk, the CPU can send a request to get the data, and the hardware will never come back. That CPU, that process, gonna get stuck there, and you never advance in the code path, right? The database will wait forever to get data to arrive, and will never do anything. It doesn't matter if you send a queue to the application, depending on the problem, it doesn't matter if you send a Q-9, it will not be able to queue. If it's a hardware issue, even a Q-9 on Linux is not able to queue. It stays on uninterruptible state. The process is there, and the only way to finish is either solving the physical problem, which usually is not possible, or rebooting the whole box, right? So, but this is an extreme case. That's not common, but sometimes it happens, but it's a very extreme case, right? But yeah, most of those things, they have the timeouts. And the timeouts, they say how long it will take to forcefully finish that operation. Does that answer my question?
Yeah. Thank you.
Yeah.
Okay, all right. So back to the connection pooling. We have many connection poolings for Postgres. So we can use the most basic one, AJ Proxy. AJ Proxy is a well-known proxy, and it was firstly designed to work with web applications, not really database applications. The thing is, it's a TCP proxy. So for AJ Proxy, it doesn't care if the packets are going to a web server or if the packets are going to a database. You just get the packets, you tell him to which server and which port on that server it needs to send the packets, and it will get the job done, right? So everything that comes here will tell for, look, everything that comes to the port 5432 here, you send to this server on the port, I don't know, 5432. And it will get the work done. And it's really fast, easy for configuration. The configuration of AJ Proxy is stupidly easy. It's very reliable. as it's really old project, been working for decades. It's really stable and reliable and fast. AJ Proxy is stable and reliable. The problem is it does not understand the database protocol. It works on TCP layer. It doesn't understand the database protocol. So we cannot we cannot split read and write queries, for example. We cannot put any rules or anything fancy or special on the AJ proxy, or you cannot even implement a authentication on AJ proxy. We can write plugins and extend the capabilities of AJ proxy, but it's a bit more complex, right? So by default, AJ proxy it just redirects the packets and the connections. So, but it does really well. It does it really well. We can work and we can have an implementation of connection pooling. We can tell for look, we can receive 1,000 connections from the client here from the application. The application can open 1,000 connections, and those 1,000 connections you're gonna send here only 100 connections. So how it does is you open the connection that arrived first will get to the database. When you reach all the 100 connections, the other 900 connections are going to stay here waiting for one slot to be available. So when one connection finishes, it will be returned to the AJ proxy, and then the next connection will be available, and will be the AJ proxy will give it to the next one in the queue, right? So have a long queue. When it's finished, another one from the queue just get to the pool and get access to the database. Basically, this is how it works. It's very simplistic. There is no much of complexity here. And depending on your application, if you only thing that you need is connection pooling, if you do not need complex logic behind those things, if you do not, it's really easy. It's possible to implement read and write split, but here you're gonna have one connection for reads and another one connection for writes. So everything that comes for the connection for read here, you can send them, but now it's job of the application to decide which connection it will open. So if the application needs to write, for example, it can open a connection here like this red one on port 5432. It's for reads, only selects. It can open another one on the port 6677, for example. Right? Everything that comes from the connection 6677, the AJ proxy can send to the replicas here. And everything that comes on the red one, that's the port 5432, it only be sent to the primary, right? This is the way that we can do this implementation on AJ proxy. Another one is the PG Bouncer. PG Bouncer is a lot more capabilities to work with Postgres connection than AJ proxy. A good thing for AJ proxy is because it's not a database connection pooling per se, it's just a TCP layer proxy. It can work with any database. It can work with MySQL, Postgres, MongoDB, any database. So this is a good thing with AJ proxy, right? And because a lot of people at work know how it works, because they've been used for web server, this implementation work with AJ proxy is a lot easier. So the pitch bouncer is knows understand the protocol from the PostgreSQL. And on the pitch bouncer level, we now can have implementation of some features that is not able on AJ proxy. For example, we can have implementation or improve the security of the database here. We can create users on the database to be used only by the PG Bouncer, and you can restrict those users to go through a specific database. So we can start creating rules inside of the PG Bouncer, right? So we can create one pooling connection here from the PG bouncer that if comes with this user, it will send that connection to the replica, or it send the connection to the primary. So we can start creating rules inside of the PG bouncer. And the other one that's really well known in the market, but it's not here in this diagram, is the PG pool. The PG pool has few advantages over PG bouncer when it's well implemented, because even though PG bouncer understands the Postgres protocol, it's not able to do the read and write query split. If you want to do, we need to do the same as we did on AJ Proxy. So we need to create one pool of connection here only for writes, and another pool of connection here only for reads. PG pool, it's able to split reads and writes. So PG pool understands the PostgreSQL protocol. It can split by itself the reads and writes. And also on PG pool, we can use caching. So PG pool has an implementation of cache that we can attach the cache and make the connection even faster. So if you have some selects that your application sends that selects all the time for the database, those will be cached on PG pool. PG pool can use memcache and can use Redis for caching, for example. Well, for Redis, I'm not sure. I think it's already using. The last time it was using memcache, but it also has its own implementation of caching. So all that data will be cached on PG pool. If you send that same select to the data application many times a second, those data can be served by the PG pool. It never goes to the database. So you start alleviating the database, and because it's in memory, it's in cache memory, it's a lot faster. It will be served a lot faster than going to the database. A common implementation that we see is something like this, but instead of having PG bouncer here, is to having PG pool. One problem for PG pool is that I personally don't like, and is how it handles connection. Just like Postgres, PG pool opens one process per connection. So it's not scalable. PG pool cannot scale for thousands of connections at the same time. It has a similar problem that PostgreSQL has. So because of that, usually we use either AJ Proxy or PG bouncer in front of PG pool. So they can receive thousands of connections. PG bouncer can receive thousands of connections. And from PG bouncer, we send the connections to PG pool. Like few connections, 100, 200 connections to the PG pool. And the PG pool can do the split, the reads and writes split. And PG pool can also have the caching here on PG pool. That works fine, works well. So as a curiosity, PG bouncer, it implements the connection not as using the process. Actually, PG bouncer uses only one process, and all the connections that come to PG bouncer, it uses asynchronous IO library to put that connection. So an example is you receive a connection for the application here, the connection comes here, and the PG bouncer sends that connection to the database. So when PG bouncer sends that connection to the database, it put in one queue and tell the kernel, look, kernel, see this network connection? Well, I want you to notify me when something comes back from this connection. So it doesn't need to, the CPU doesn't need to keep spinning to check if something comes all the time on that connection. It really stays there doing nothing. So use zero CPU resources. When something comes on the network, The network will notify the kernel, and the kernel will notify the PG bouncer, look, you need to wake up because we have something from this connection. And then PG bouncer will return this thing to the application. So this implementation is really powerful because we can handle thousands of connections. And just because we don't need to keep looking if the database replied back, so we can leave all those thousands connections like on the queue, and when we have something from the database, we just get what you have, get the next connection, put in the queue again, and you come back. Even the context switching here works in a way that's a lot better control than if we are having connections working like either process or even threads. So this way of implementing the connection works a lot better and is way more scalable. And that's why PG Bouncer scales a lot better when we have hundreds of thousands of connections than PG Pool or even the database. This is why it's so fast, so powerful to have solutions like PG Bouncer. Another proxy that it's new in the market, and it's really really cool though. How is the name? Just a second, I forgot the name. I'm getting here. It is. GitHub. Let me go to GitHub here. Goodness, how is the name? PG Agro. This is another a new project. They work in a fashion way like PG Bouncer of implementing things. But for those ones that are starting and want to learn how those things work and want to hack into the code, the code of PG Agro is a lot simpler to understand than the code of PG Pool and PG Bouncer. So it's a nice implementation. They have a nice implementation. I've seen some companies that are starting using. It's not so popular like PG Pool and PG Bouncer because they are for decades in the market. PG Bouncer was firstly developed by Skype. It was a product that they built to solve their own problem they have. PG Pool was developed long ago, even before Postgres had the built-in replication. So one problem that PG Pool was intended to solve, PG Pool 1 was intended to solve as well, was to have replication from Postgres. That's why it we're still able to send data for multiple servers using PG Pool. Not sure if it's useful anymore. So I've seen some people trying to make nice stuff, but they create a lot of problems. So be careful when using those fancy features in your implementation. And thing is, at Percona, we support AJ Proxy, PG Bouncer, and PG Pool. So we support those three. Especially PG Pool, we have developers in-house. So one of the main developers of PG Pool work with us here at Percona. But we also support PG Bouncer, and we really usually recommend depends on your architecture, PG Bouncer, and sometimes, as I mentioned, PG Bouncer together with PG Pool, it can give a really good result. Well, we don't have time to go for some demos here, but the configuration of them is really, really simplistic. We don't have much, there is no much to do in the configuration. It's very simple, and that's it. I hope we learned something today, and it was enjoyable.
Yeah, it was great. Thank you so much for your time, Charlie.
Yeah, talking too much as usual, right?
No, it's okay.
Thank you so much for sharing. I always was I was interested in learning more about connection pool because I'm working on a project that that I recently implemented multiprocessing, but I have this problem that how do I implement connection pooling for all the queries that I need to execute. So what you shared today would really help me to have a better idea on how to solve that.
Cool.
So thank you.
Nice.
Yeah. Do we have another session, Charlie, in another time, or this is the last for this month?
We have this session every 2 weeks, right? So every other week we have one. So in 2 weeks we have another one. I don't know what's gonna be the topic, but yeah, we do. We already have a calendar, a whole schedule for sessions up to the end of the year. Every other week we are here to talk that much and bother people a little bit about database, especially Postgres.
Yeah, this is nice. I'm learning Postgres now, so it helps a lot.
Cool.
Thank you so much for this. Yeah.
You're welcome.
Well, we don't have any questions in the chat, so I think we can finish. And really, I really thank everyone who joined us today, and I hope that you learned something from this session. Charlie shared some interesting tools that I think we need to start checking. So thank you so much for that, and thank you everyone who joined us. See you next stream.
Thanks,
See
everybody.
you in the next one. Bye bye.
Yeah, bye-bye.